Hello friends, welcome to CEC live lectures. Dear friends, from today onwards we are going to conduct series of lectures on laser physics. This is the first and introductory lecture where we are going to discuss more and more on laser physics, what laser physics is, as well as some other important concepts and elements of the laser physics too. Friends, for the discussion on topic, we have with us in our studios Dr. Sonia Bansal. Dr. Sonia Bansal is assistant professor and she is a professor of physics and teaching in one of the leading institutions of the country. Friends, we always welcome you through our live platform and we believe that your feedbacks are important. Friends, if you wish to become part of this live session, then you can contact us through our toll-free number. You can ask questions through our toll-free number. Our number is 1800-110-430. I repeat, our number is 1800-110-430. You are just requested to call in the last 10 minutes of the lecture only. Now, I would like to welcome our guest, Dr. Sonia Bansal, once again. Hello, ma'am.
Thank you, Vidya. Thank you. Dear students, we will discuss about the laser physics. This is the first series of laser physics. We will define the basic phenomena which are behind the laser physics, and then we will discuss about the characteristics of the laser physics. Then we define what are the features which describe the light as a laser. What is a laser? Laser means light, as name suggests, L-A-S-E-R, light amplification by stimulated emission of radiation. That is the laser. This laser light is different from the ordinary light that we will discuss in this lecture also. After that, we will define the basic phenomena behind the laser physics. First, we start with the quantum nature of the light. As we know that the quanta was explained in 1900 by the Max Planck, which explain that light consists of discrete bundles of chunk and each is having the energy h nu, and this packet of energy is known as the quanta. In 1905, Einstein refined the quantum hypothesis and gave the name photon to the quantum of light energy. It means this quanta is named as a photon by the Einstein in 1905, and these photons play a very important role to define the quantum nature of light. Photon represent the minimum energy unit of the light. It means it defines the very minimum energy of the light, that is in terms of h nu. Here we see the energy of the photon is defined as E is equal to h nu. It is localized in a small volume of a space and remains localized as it moves away from the light source. It means its energy will not change. It will be E is equal to h nu. It means a single energy photon is defined by h nu. The light energy rho nu, that means with respect to the frequency, that is nu is defined the frequency, h is the Planck's constant, emitted by a source must be integral multiple of photon energy. Then we define the light energy rho nu is equal to nh nu. As we know that here we see that nu is the frequency of light, and here we define the light energy with respect to the frequency, and maybe as we define it is must be the integral multiple, it will be discrete value. So n value is 1, 2, 3 and so on. It means for the one photon is defined as h nu, for the two photon is defined as 2h nu, and 3 photon is defined as the 3h nu and so on. Now, interaction of the radiation with matter is better explained using the concept of photon rather than by the wave concept. It means we define the interaction of radiation by the phenomena of the photon, except the wave concept. Now, energy exchange can take place only at a certain discrete values for which the photon energy is the minimum energy until that light can give or accept. It means the wave picture of the light in the classical and the photon picture in the quantum mechanical. Photon picture in the quantum mechanical means we are defining a particles of the size atomic. Laser is inherently a quantum mechanical device because its operation depends on the existence of the photons. It means when we define the laser, then we define the quantum mechanical phenomena, and then this depends upon the existence of the photons, how the photons behaves in the quantum mechanics. That by using that we define the laser physics. Now, interaction of light with matter. As we all know that the Maxwell, which defined the light, belongs to the group of electromagnetic waves, propagates with the speed c, which is the maximum speed in the vacuum. Then the frequency and the wavelength related to c through this relation, c is equal to nu lambda. We all know that the speed of light is equal to frequency into the wavelength of light. Then when the incident on the substance, when this light is incident on the substance, may undergo reflection, transmission, absorption and scattering to varying degrees depending upon the nature of the substance. The result in the loss of energy and hence decrease in the light intensity with the distance. As we see here, this is the input wave and this is the absorbing medium. Light is absorbing by the some material or the some medium, then the output will be of the decreasing intensity with the distance as the distance increases. That is the attenuation coefficient, which measure of the absorption of light in an optical medium. This is an optical medium, how much light is absorbed by this material, defined by the attenuation coefficient. Now, the light intensity I at a distance x in the medium, we will define the how much intensity is absorbed, that by the intensity of light at any distance x. Here we see that this is the distance x, and I naught is the incident light with the intensity I naught falling upon a absorbing medium or active medium from air to the another medium. Then we see that the light of intensity I naught fall upon a medium. Then this I, which absorbed by the medium, the light intensity absorbed by the medium is defined by I is equal to I naught e power minus alpha x, where alpha is the attenuation coefficient, x is the distance, I naught is the incident light and I is the absorbed light. Then where light intensity decreases exponentially with the distance in the medium. When the light beam encounters obstacles which have sizes smaller than the wavelength, it means when this absorbing medium is having the size which is less than the wavelength of light as defined d very less than lambda, it is redirected into the different direction, and that is known as the scattering. Scattering phenomena also causes attenuation of the energy. Again, it explains the absorption of the energy and is described by the exponential law, which is defined as I is equal to I naught e power minus alpha s x, where we know that alpha x is the scattering coefficient. Attenuation of the light due to the both the absorption, the previous equation, and the scattering effect is defined as I is equal to I naught e minus alpha a, this is for the absorption, plus alpha s, this is for the scattering, into the x for a particular distance absorption. Now, the intensity when the light is absorbed by any medium, the two processes takes place. Number one is the absorption and second is the scattering, and that defined by the intensity I is equal to I naught e power minus alpha a plus alpha s into x. Here we see that the intensity will decrease exponentially when the light is absorbed by the medium. Now we discuss about the distribution of atoms, how the atoms are distributed in the different energy levels. As we are talking about the laser, and we will be talking about the absorption, emission and the stimulated emission, that only defined by the how much atoms and molecules jump from the lower state to the higher state. Now here distribution of the atoms, how the atoms are distributed to define the laser. Then here we define the energy levels. We require the energy levels permitted orbits with the specific amount of energy, which are allowed energy levels through which the atoms can jump from one state to the another state. Then these here in the diagram we see that here we are having a different orbits, or n is equal to 1, orbital number 1, 2, 3, 4, 5, 6 and so on. These are the electron orbits, and the center is the nucleus. And here we define the electron orbit represent the energy level diagram. Here we see that the ground state defined by the n is equal to 1. Another state, which is the excited state, defined by the n is equal to 2, which is another energy level, and this is another energy level, n is equal to 3, n is equal to 4 and so on. This is the orbital level diagram, this is the energy level diagram. Here we define the energy levels. We require the two energy levels. First is the ground state and second is the excited state. These all are the excited state levels, and this is the ground level, or we can say it is a ground state, and others are excited states. What is a population? Population means, as we talk about the atoms, then we can say population is the number of atoms per unit volume that occupy a given energy state. Then population defined by the capital N of an energy state depends on the temperature T according to the Boltzmann equation. Then we define n is equal to e power minus e by kt, where k is the Boltzmann constant. Atoms distributed frequently in the different energy state. Then we can get the emission and absorption. When the electrons or atoms are distributed in the different energy levels, then the absorption and the emission takes place. We define the laser phenomena. Tends to the atoms distributed differently in the different energy states tends to be at the lowest possible energy level. Now, what is the requirement for the laser? It is the basic point which is used to define the laser system is a thermal equilibrium. At temperature about 0 Kelvin, atoms always have some thermal energy. What I am saying that here we see that at the 0 Kelvin temperature, atoms have some thermal energy and distributed among available energy levels according to their energy. Means all atoms are distributed in the different energy levels according to their energy. At a thermal equilibrium, the population at each energy level decreases with the increase of the energy level. Here we see that this is the population or the lower level. This is the ground level. As we move forward towards the higher energy level, we see that its energy level decreases. The population at each energy level decreases as we move from lower state to the higher state. Then here we define the two electron system. This define the energies from level 1 to the level 2. This axis define the energy, and here we have the population of level 1, or we can say it is a ground level and having the population N1 with the energy E1. This is the excited level having the energy E2 and the population N2. This define the two level system with the different energies and with the different population at the two levels. For the in the next we define the two energy levels E1 and E2, and accordingly that we define their population. The population can be computed by the Boltzmann equation, and the ratio of population N2 by N1 is called the relative population. It means when we define the population of two levels, then we define the ratio between the upper level to the lower level. Number of atoms at the upper level divided by number of atoms at the lower level, which was defined by the E power minus E2 minus E1, energy of upper level, and the energy of lower level divided by KT. K is the Boltzmann constant and T is the temperature. It means distribution of the atom according to the energy, thermal T is the temperature. Now we can define N2 is equal to N1 e power minus delta E divided by KT. We can write E2 minus E1 as delta E. So this equation we can write it as N2. N2 means number of population at level 2 is equal to N1 e power minus delta E divided by KT. All depend upon the level 1 energy, number of atoms at the level 1, energy difference between the two level, and the temperature. Boltzmann constant is the constant quantity. The relative population N2 by N1 depends on the two factors, as I discussed, that energy difference, which is E2 minus E1, and the temperature T. It means the population difference between the two levels depends upon the energy difference E2 minus E1 and the temperature T. Or we know that at the room temperature all the atoms in the ground state. At the higher temperature, as the temperature will increase, the atoms moves towards the higher state and it will go from the ground state to the excited state or to the higher state. Now in the material at the thermal equilibrium, more atoms in the lower energy state and then in the higher energy state. The fraction of atoms would be large if the energy levels are close or temperature is large. Then there are the two limiting cases. When E2 minus E1 is equal to 0, then number of population of the lower level will be equal to the number of population of the upper level. It means both are equally populated, both the energy levels are equally populated. When the temperature approaches to infinite, again N2 is equal to N1. It means the number of population of both the levels are equal. Now from this we have the important conclusion that as long as the material is in the thermal equilibrium, the population of the higher state cannot exceed the population of lower state, as if we are talking about the thermal equilibrium. The population of higher state cannot be exceed the population of the lower state. It means the lower state are more populated, lower state is more populated as compared to the upper level in the thermal equilibrium condition. Now the another which will be important for the laser physics is the excitation and the de-excitation, or we can say absorption or the emission. What is the excitation? Electron in the ground state receives an amount of energy equal to the difference of the ground state energy and one of the excited state energy and jumps to the excited state. That is the excitation. It means the electron which are going to jump from lower state to higher state must have a energy of E2 minus E1. And this energy is known as the photon energy, which is h nu is equal to E2 minus E1. Induce electron transition from the energy level E1 to E2. And induced, or this is called the stimulated absorption. It means for an atom to jump from lower state to the higher state, it is required amount of energy. That energy is h nu, and this phenomena is known as the induced absorption or stimulated absorption. Now here we see in the diagram, here we see this is the excited atom. This atom is at the lower at the ground state and it jump to the higher state. Then this is the exciting atom and this is the emitting photon. This exciting atom, it requires the energy to go from the ground state to the first excited state, and this energy is known as the h nu. And here this is the emitting photon, means the electron jump from higher state to the lower state. It means de-excitation. Then we can say that photons will be emitted. here we see that only the mechanism is through the emission of the photon takes place is known as the de-excitation. The emitted electron emits a photon of energy, again h nu is equal to E2 minus E1. The jump from the excited state, this is the excited state, this is the ground state. Here we see from this diagram, E1 is the ground state, E2 is the excited state. The atoms or the electrons jump from the E1 to E2, this is the excitation, and it requires the energy h nu. And when it jumps from higher state, means E2 to E1, it radiates energy of E2 minus E1. And this phenomena is called as the spontaneous emission. And there are the two features that electrons cannot stay in the excited state for a longer time. It means when the electron jump from lower state to the higher state, then spontaneously it will come from E2 to E1, higher state to the lower state, as it could not stay for a longer time at the excited state. It has to get rid of the excess energy in order to come to the lower energy level. It means the radiation will comes out when it have to radiate excess energy when it is jump from the higher state to the lower state, and this phenomena is the emission. Now we start with the laser. What is the laser? Up to now we have discussed the features which will be used to define the laser physics. Now here today we will define the laser. What is the laser? Laser is acronym of light L, amplification A by stimulated S, emission E of radiation R. LASER. It means laser is the light amplification by stimulated emission of radiation. One of the outstanding invention of 20th century which defined the light source, but it is very much different from the traditional light source. Laser light source is very much different from the ordinary light source, not used for the illumination purposes. Widely used as a high power electromagnetic beam rather than the light beam. It means it is not used for the illumination purpose or for the light beam, it is used only for the high power electromagnetic beam. Now here we discuss about the difference between the common light and the source versus laser. We see that ordinary light having the many wavelengths, but the laser light having the monochromatic, means a single wavelength. Ordinary light multidirectional, but the laser light is highly directional. Ordinary light is incoherent, but the laser light is highly coherent. We will define one by one these characteristics. Now laser beam having a different characteristics, in which we define the laser light differs from the ordinary light emitted by the conventional sources. Most striking features of laser light which distinguish it from the ordinary light are directionality, high intensity, high coherence, highly monochromatic. Highly monochromatic means define the single wavelength. Laser light can be produced as a polarized light, can be generated as a very short pulse at high powers. These are the characteristics of the laser light. It means laser light is highly directional, high intensity, high coherence and monochromatic. Highly monochromatic means having the single wavelength. All lasers are having a single wavelength light as it is emitted by the laser. The two parameters which cause the beam divergence. Highly directional. For defining the highly directional, we have to define it is highly divergence. Then the two parameters which cause the beam divergence, first define the size of the beam waist and second is the diffraction. By this we define by the full angle divergence, which is given by 2 theta is equal to 4 lambda divided by pi d naught. 2 theta, define this theta, how much it will be divergence, and this d naught, define the 2w naught is the diameter of the beam waist. This is w naught, and for this we can calculate the twice of w naught, define the d naught, and the divergence is inversely proportional to the d naught. It is large for the beam of small waist. If the beam having a small waist, it means W, then the value of D naught will be large. It means the laser beam is highly divergent. The beam divergence due to the diffraction is determined from the Rayleigh criteria that define theta is equal to 1.22 lambda by d, where d is the diameter of laser aperture. Then in case of the gas laser, the diffraction divergence is about twice as large as the beam waist divergence. A typical value of the divergence for helium neon laser is theta must be 10 power minus 3 radian, that the laser beam diameter increases by about the 1 mm for every meter it travels. Its size will be increases, the diameter will increases. Beam divergence of large laser is approximately micro degree, that is of the 10 power minus 6. A laser beam of 5 centimeter diameter, when focused from the earth, spread to the diameter of only about 10 meter on reaching the surface of the moon. It means it will diverge from 5 centimeter to the 10 meter. Then an extreme collimation has been taken place by the laser beam. Thank you.
With this note, thank you, ma'am. Thank you so much for giving this session on laser physics. Friends, we believe that your feedbacks are important for us. So if you wish to become part of this session, then do call us through our toll-free number, as we will be back after a short break and would be discussing more. And in that session, of course, you can become a part of it. You can participate in it by asking questions. So here we are taking your leave with the promise that we are back after a short break. Thank you. Hello friends, welcome back to this session. Friends, as you know that today we are talking on laser physics. We are trying to understand what laser physics and what is laser physics is and what are the characteristics of laser physics. For the discussion on the topic, we have with us in our studios Dr. Sonia Bansal. Dr. Sonia Bansal is assistant professor in Department of Physics by MCA University. Friends, we know that you have lots and lots of questions. So if you wish to become part of this session, if you wish to ask questions, then do call us through our toll-free number. Our number is 1-800-110-430. I repeat, our number is 1-800-110-430. Now I would like to welcome our guest, Dr. Bansal, once again. Hello ma'am, welcome to the session.
Thank you. Dear students, we are talking about the laser physics, and presently we are discussing about the characteristics of the laser. How the laser light is different from the ordinary light. That laser light is highly directional. Number 2, laser light is having the high intensity. Laser light is highly coherent. laser light is highly polarized as compared to the ordinary light. One by one we are discussing it. Now we come on the intensity. That laser light is highly intense light. How we define that it is a highly intense? That we define by the I is equal to 10 power by lambda whole square P omega W meter minus 2. Intensity define the power output of a laser may vary from a few milliwatt second to a few kilowatt second. The energy is concentrated in the beam of a very small cross section that define the high intensity. The intensity of laser beam is approximately given by this formula, where P is the power radiated by the laser. This define the intensity of light depend upon the power that we define by an example. In case of 1 milliwatt helium neon laser of the wavelength 6328 into 10 power minus 10 meter, then the I is defined as intensity is defined as 2.5 into 10 power 11 watt meter minus 2. To obtain the same intensity from a tungsten bulb, temperature have to be raised to 4.6 into 10 power 6 Kelvin. The normal operating temperature of the bulb is 2000 Kelvin. It means to get this much power or this much intensity from the ordinary bulb, we require this much energy. 4.6 into 10 power minus 6 Kelvin temperature we require to get this much intensity of the tungsten bulb. But the laser light gives this, but the helium neon laser give this intensity. Now brightness. The laser light is highly brightness. The brightness of sun at temperature 6000 Kelvin. The B brightness defined is 1000 watt centimeter minus 2. Then brightness of the 1 milliwatt helium neon laser can be calculated by lambda is equal to 6328 into 10 power minus 10 meter. Then the brightness of helium neon laser is 3300 times greater than that of the brightness of sun. Due to the high emittance, laser beams are not allowed to see directly because it is very harmful. From this equation we can see that the helium neon laser is highly bright as compared to the sun. By we can say that the brightness of the helium neon laser is 300 times greater than the brightness of the sun. Now conventional light source are incoherent. This is the very important characteristics for the laser light, that it is highly coherent. The conventional light source is incoherent. That light that emerges is a combination of photon in a random manner. But in the laser, it is not in a random manner, but it is in a phase. Then laser means coherent. The lasers are highly coherent. The output that emerges is a resultant of a large number of identical photons which are all in phase. The coherence requires that there is a connection between the amplitude and the phase of the light at one point and the time, and the amplitude and the phase of light at another point of time. It means when we define the coherence, then we require the amplitude and phase of the light must be coherent for the one time, and it will be on the another time also. For the coherence, we define the two classes of coherence. Number one is the temporal coherence, that define the longitudinal coherence, and second is the spatial coherence, that define the transverse coherence. In the temporal coherence, the consistency of and the predictability of the phase as function of time, temporal related to the time, when the waves travel along the same path at slightly different times, same path at the slightly different time, and they are highly temporal coherence. Spatial coherence, transverse coherence, where we reference the phase relationships between the waves traveling side by side at the same time but at the some distance from one another. It means that there is some space. Spatial means there is some, this phenomena depend upon the space. Means we are defining the waves traveling side by side at the same time but at the some distance. The waves are moving at the different space. That define the spatial coherence. Now here we see from the diagram that temporal coherence, same phase for any time interval of the same duration. Here we see that T2 minus T1, but they are all in a phase. Illustration of the temporal coherence defined here. For the T2 minus T1 is equal to T4 minus T3. If phi 2 is equal to phi 1, that define the temporary coherent waves. L coherence, length of the coherence up to where we can get the coherence that defined by the L coherence, which is equal to lambda square divided by 2 del lambda. It means the length depends upon the wavelength of the light, and the temporal coherence characteristics by the two parameter. First is the coherence length, that is L coherence, that defined by the lambda square by 2 del lambda, and the coherence time that defined by the T coherence. And this fluorescent tube, the L coherence defined by this value 5040 angstrom. The sodium lamp, this value is 0.29 mm. For helium neon, its value is 100 meter. Then both measure how long light waves remain in phase as they travel in the space. That define the coherence of the light. Means all the two waves are in a phase up to certain distance. The monochromaticity, a measure of the temporal coherence. It means we define the monochromaticity by the temporal coherence. Spatial coherence, the phase difference remains same for all. Here we see that the phase are the same. Yeah, P1, P2 are the different positions, and here again the P1, P2, but these waves are moving in the same phase but at a different time. The spatial coherence measure the area over which the light is coherent. The spatial incoherence arises due to the size of the light source. Here we define the 2 point which define the light waves from a point source producing ideal spherical wave fronts maintain spatial coherence. From the point P1 to the P1 and P2 have the same phase, but here extended source produces wave fronts far from ideal. Then the point P1 and P2 do not have the same phase, leading to the spatial incoherence. These are the incoherence example. This is the coherence example. All are in phase from P1 and the P2. Now the next characteristic is the monochromaticity, which is defined by the coherence. Then the light coming from the source has only the one frequency of oscillation. The monochromatic light from a monochromatic source, that is a laser. In practice, not possible to produce a light with only the one frequency, but here in the laser we are having the light with the single wavelength. The light from the any source consists of a band of frequency del nu, closely spaced around the central frequency mu naught. Here we see that this is the del nu, and the conventional sources del nu approximately equal to 10 power 10 hertz or the more. But in the laser light, the light from the lasers, it is 100 hertz. The difference between the del nu means the frequency difference must be the 100 hertz, means they are highly monochromatic, having the single wavelength. This band gap is very less in the laser light. Now the best feature is the polarization. As the laser light is highly polarized, the light waves, electric and magnetic fields vibrating perpendicular to each other and to the direction of propagation. Then the polarization measures the alignment of E energy and the E for the electric and the M for the magnetic field in a light wave. Then we define the linear or the plane polarization of the light. Linear polarized light beam, it is orientation of the electric field remains in the one plane or a single plane while its magnitude changes with the time. Any other type of polarized light, a result of the superposition of two linearly polarized wave having the electric field perpendicular to each other. That is, the conventional light sources are the unpolarized light, but the laser output may be unpolarized or polarized. They may be in the phase or they may in the not in a phase. Now, to define the laser, Einstein explained some predictions. From this we define it that in the Einstein prediction in 1917, Einstein predicted that there must be a second emission process. Up to now we have discussed that absorption, excitation and the de-excitation, means absorption and emission takes place. Excitation by absorbing energy, de-excitation by releasing energy. That is also known as the absorption, energy absorbed by the atoms and go to the higher level, and the emission, energy released when the atoms jump from higher level to the lower level. The first phenomena, absorption, takes place induced because energy is required to jump the electron from lower level to the upper level. And the second phenomena, that is the de-excitation or emission, is the spontaneous emission, means electrons cannot stay for a longer time at the upper level, so the electrons or the atom will jump from higher level to the lower level spontaneously. That's why it is called a spontaneous emission, and this spontaneous emission release the energy. But Einstein in 1907 explained that apart from this, there is a one process also considered for the laser system, that is the second emission. What is this second emission? This second emission is the stimulated emission, which plays a very important role to get the laser beam. Now, from here we discuss about what is this second emission, what is the stimulated emission. Now, in 1917, Einstein predicted that there must be a second emission process to establish the thermodynamic equilibrium. Means atoms move to the excited state under action of incident light. Means the atoms will move from lower state to the higher state. The excited atoms return to randomly to the lower energy state, means that is the emission. First is the absorption and second is the emission. It is likely that the stage may be reached when all atoms are excited. That is the violation of the thermal equilibrium. It means the atoms are at the higher level, but it is the violation of the thermal equilibrium. It means that the lower level in the thermal equilibrium, we have the lower level or the ground level having the higher energy as compared to the upper level. But here, because of the third process is the stimulated emission, here we see that there is a violation of the thermal equilibrium condition. Means upper level, all the electrons, all the atoms jump to the higher level, and the higher level are highly populated. The Einstein suggested that there could be an additional emission mechanism by which the excited atoms can make downward transitions. Means when all the atoms are at higher level, then there must be a de-excitation by the emission mechanism. That mechanism is known as the stimulated emission. Predicted that the photons in the light field induce the excited atoms to fall to the lower energy state and give up their excess energy in the form of the photons. Again, the electron jump from the higher level to the lower level, it will emit energy. In the previous In the spontaneous, it will generate energy, and here in the stimulated, it is also generate the energy when it's come from the higher level to the lower level. So for the laser system, we define the three processes. To get the laser light, we define the three processes. Consider a medium consisting of identical atoms in thermal equilibrium having the energies E1 and E2, population N1 and N2. Here we define the two systems. From this diagram we see this is the energy difference between the two levels. This is the lower level or the ground state level, and this is the excited state level. The ground level having the energy E1, the excited level having the energy E2, and the population of this energy level is N1 and the population of this energy level is N2. Now the three processes are the absorption, or we can say stimulated absorption. The second is the emission, spontaneous emission, and third is the stimulated emission. Means we are having a one absorption and two emission. Now first, one by one we will discuss. First is the absorption. What is the absorption? Atoms in the lower energy level E1, here we are having the energy in the lower energy level E1, absorb the incident photon, this incident photon of energy h nu, which is equal to, whose energy is the E2 minus E1, incident photons, and jump to the excited state E2. Here we see that this is the atom in the thermal equilibrium. In the previous, when the energy h nu is given, it will absorb energy and jump to the higher energy level, that is the E2. Then it is defined by A plus h nu. H nu is the energy required to absorbed by the atoms jump to the higher state. The A plus h nu is equal to A star. This is known as the induced or the stimulated absorption. For this, the rate of absorption is defined as AR, rate of absorption defined as RABS is equal to B12 rho nu N1. Every term have its meaning. B12, it's the constant of proportionality, and it also known as the Einstein coefficient for induced absorption. It indicates the probability of an induced transition from the level 1 to the level 2. It means B12 is the Einstein coefficient for the induced absorption. Second is the rho nu. Nu is the frequency. Here we define that rho nu is the energy density of incident light which is absorbed by the atom to jump from lower state to the higher state. And what is N1? N1 is the population at lower level of energy E1, and this is the rate of absorption defined by the RABS is equal to B12 rho nu N1. This is for the absorption equation. Now second is the spontaneous emission. As we know that the atoms are at the higher level. Now it will jump to the lower level spontaneously. An excited atom can stay in the excited level for an average lifetime tau spontaneous. It means up at the higher level, electrons can stay only for a fewer time, or the average lifetime that was defined by the tau sp, and it is not stimulated by any other agent during this short stay. It means the electrons can stay only for a shorter time at the higher level. So excited atoms undergo a transition to the lower energy level at its own by giving excess energy in the form of a photon. It means the atoms are at the higher level, jump to the lower level by releasing its energy. Here we see diagram that E1, E2 energy states, the atoms jump from the higher state to the lower state and the emitting photons are ejected. That is defined by the h nu is equal to E2 minus E1. Now the A atoms defined by the A plus h nu, as this is having the energy and it is releasing the energy, that is equation will be A plus h nu, and that is known as the spontaneous emission. The rate of spontaneous transition is defined as RSP spontaneous is equal to A2 1 and 2. Simply we don't require any energy to jump the electron from higher state to the lower state. So here there is no need of rho nu, because we not require any energy to jump the electron from higher state to the lower state. So this equation is very simple. We define by RSP is equal to A21, from 21 means from upper level to the lower level, second level to the one level, and to define the energy number of atoms at the upper level. So A21 again define the Einstein coefficient for the spontaneous emission and is the function of frequency and the properties of the material. The probability of spontaneous transition from the level 2 to 1, and we define A21 means Einstein coefficient of spontaneous emission is defined by 1 by tau sp. Tau is the lifetime, represent the lifetime of the spontaneous emission, means at how much time the electron can stay at the upper level and it will spontaneously come to the lower level. Then what is N2? N2 we know that the number of atoms at the higher level or the population at the higher level. The important feature for this is the no outside control in the spontaneous emission. The probabilistic in nature, automatically the electron will jump to the higher state, the lower state, because it cannot stay there for a longer time. The light is incoherent light because all are not in a phase, they are randomly moved, not monochromatic, lack of directionality. It means we are getting the ordinary light by the spontaneous emission. Incoherent radiation result for the superposition of the wave trains of the random phases. Here we see that these all are the example of the spontaneous emission. Net intensity is proportional to the number of radiating atom. So I total is equal to Ni. Dominates in the conventional light sources. Thus, the spontaneous emissions are defined the conventional light source. But here we define the third point, which is the stimulated emission, which is very important, which plays a very important role for the laser light. What is a stimulated emission? An atom is excited state need not to wait for a spontaneous emission to occur. If the photon with the appropriate energy h nu is equal to E2 minus E1 interact with the excited atom, it can trigger the atom to undergo transition to the lower energy level to emit another photons. It means that atoms are at the higher level. Now it is triggered by the another photon which is of the energy h nu E2 minus E1, and it will interact with this atom and it will stimulate it to jump from higher level to the lower level by releasing amount of energy. The process of emission of the photon by an excited atom through a forced transition occurring under the influence of external agent is called the induced or the stimulated emission. Here we know that the atoms are jump from higher level to the lower level not automatically but by the induced processes, and that is defined by A plus h nu is equal to A, which is equal to 2 h nu. It means it will generate the higher energy as compared to the triggered energy. The rate of equation of the state emission is defined by RST is equal to B21 rho nu N2. Again B12 is the Einstein coefficient for the stimulated emission, N2 number of population state, and rho nu is the energy density. Thank you very much. Thank you, ma'am.
Thank you so much for giving this progressive and productive session. Friends, we know that you have lots and lots of questions which you were not able to get or ask through the session. Then you may try our ID also. You can post your questions there, and we'll try to give answers to your questions when next time Dr. Sonia Bansal visits our studio. So do write to us at info.cec@nic.in. We are going to meet again soon. Till then, take care. Goodbye. Thank you. Thank you.
Thank you.